Hello everybody, we are discussing GPU computing module in the course of high performance computing for scientists and engineers, and this is the lecture on introduction to CUDA programming, which we are continuing from last class. In last class we discussed about few aspects of CUDA programming. We first discussed how to install and compile CUDA and execute a CUDA program, and then we looked into a sample program. We will continue from there. This is the sample program, which is our first CUDA program we have looked into last class. So, this is a program for vector addition. The idea of this program is that we will take two vectors of relatively large size. So, each of these vectors have 10,000 elements, 100,000 elements in our example, and we will write a CUDA C program to add these two vectors and get a resultant vector, and the addition will be done by CUDA kernels, in a sense that each of the threads in CUDA will be in CUDA program will be responsible for adding each of the elements in the vector. So, in parallel multiple threads will be launched and multiple elements will be added together. This is quite similar to the concept of vector processing, at least this programming model, which we have seen earlier when we were discussing fundamentals of parallel computing. So, if we look into the program, it has it is a single file with an extension .cu. So, the program is some program name, say vcadd.cu, that is the program name. And if we look into that file, it has two components. One is the portion which will be executed by CPU. It is the main program, and this is most likely a C code with some of the CUDA constructs inside it. And then there is another one particular instance in this program which writes execute the kernel, and this executes a kernel vcadd, and we write that this is a function which will be called by CPU and that will be executed in the GPU. So, this kernel is a function which is called by the C program, and this function will be executed by the GPU. So, we will look into the function name, and there is a specific syntax for this function calling. We will look into this syntax in more detail. If we look into the function name vcadd, and we will see that the next part of the code is the vcadd function, which is CUDA kernel, and it starts with an execution syntax __ global __, and then it is a function of void type, so it cannot return anything. We can understand, and this is executed by GPU now. So, this is the function which is called by the CPU and will be executed by the GPU. So, CUDA will launch this function in parallel in multiple GPU cores, and different threads will be active then. Well, this will typically return a void because GPU and CPU memories are different. Whatever we are executing in CPU or whatever a programmer is writing, that code will primarily take information from CPU RAM and will be executed in CPU. So, whatever is executed in CPU will write to the CPU RAM and cannot read from the GPU memory. Therefore, when a function is called from the CPU, it must return a void to the, when a function is called from the CPU to run in the GPU, it must return a void. It cannot return a memory. Memory can flow from CPU to GPU only through CUDA memcopy. So, if we look into this function, int id gives the particular id of each thread, and based on the id, if the id is less than n is the size of the vector, based on that id, elements of A and B are added and element of C is obtained. So, once this kernel is executed on the specific number of threads, and the number of threads are specified by grid size and block size, then that will write to the vector C, which is passed as d_c, that is in that CUDA's, in the GPU's memory d_c, and then d_c or device C will be copied to host C or CPU C, and then only we can read it from the C program that we are writing executing through the CPU. So, first part will be the vectors which we are allocating in the CPU, assigning in the CPU, the initialization of the vectors. These vectors will be copied to the GPU, then function will be called by CPU which will be executed in the GPUs in multiple threads, and then the function will return a void, but it will do certain change in the GPU memory, which is device underscore c, d underscore c, this lies in the GPU memory, and then data will be copied from GPU memory to CPU memory, and then if we want to do some processing with that data, we can do that. Well, we can identify, we have discussed about this program in the last class also. Now we can identify that there are two important instances in this program. One is that kernel calling, that this function is called as a kernel, which will be executed by the GPU and called by CPU, and then this kernel function itself, which is executed on GPU, not in CPU. And we can identify that there is a specific syntax for kernel calling, and there is a specific syntax for identifying the kernel. We will look into these things. And also a kernel takes some of the arguments which are memory locations in the GPU, and some arguments are given within a brace, which gives the number of blocks inside a grid and number of threads inside a block. So in total how many threads will be launched, that is also specified here. So a kernel is defined using underscore global underscore declaration, and this is called an execution space specifier. It specifies what is the execution space. This declaration specifies what is the space in which this function will be executed. Will it be executed in GPU, will it be executed in CPU, etc. This particular this particular statement specifies that execution, and the number of threads that execute the kernel, that is specified using execution configuration syntax. And what is execution configuration syntax? Which is present inside the brace with the kernel call. So if we look into the program, when we ask call the function vacadd and within brace grid size, block size, and pass the variables, then this becomes the execution configuration syntax. So this becomes the execution configuration syntax, which specifies how many threads will be running there, and each thread that executes the kernel will get a unique thread ID, which is accessible in the kernel through built-in variables. So when we call the kernel, it is identified by the execution space specifiers. Execution configuration syntax is specified with the kernel call. Execution space specifier is specified before we write the kernel function, at the beginning of the kernel function. And once we look into the kernel function, it knows what is the size number of threads in a block and what is the number of blocks in a grid. So what is the total number of threads it knows. Based on that, it finds the global thread ID, and each kernel has its own global thread ID, which is obtained via the ID of the block, ID of the thread, and dimension of the block. Dimension is what is the total number of threads in the block. And then based on the particular thread ID, a thread operates on certain part of the memory allocation of the C vector. That is it. So we need to identify what is, we need to look into detail what is execution space specifier, and this is our execution space specifier underscore global underscore, which is present in the kernel function, and what is execution configuration syntax, which is called which is written during the kernel call. When the main program calls kernel, the execution configuration syntax is given there. These two things have to be looked into, and everything we are discussing here is taken from NVIDIA CUDA programming guide, because CUDA is developed by NVIDIA. So whenever we look into details of CUDA, details of syntax and semantics of CUDA, we have to look into NVIDIA's CUDA programming guide. And this ID gives unique number for each thread. So this ID of the thread which is executed by one particular GPU core during the kernel execution is obtained by the built-in functions of the CUDA kernel, and based on its local block ID, local thread ID is based on the block ID, local thread ID, and the dimension of the block. And we will look into how to find out the kernel IDs in more detail when you look into thread algebra. The kernel function is executed into grid size into block size time, because grid size is the number of blocks inside the grid, block size is number of threads inside a block. So, how many threads are launched? Each block launch block size number of threads and grid size number of blocks are launched. So, total grid size into block size number of threads are launched and each thread calls a kernel. So, kernel function is executed in grid size into block size times. However, the given vector has a dimension n. So, n can be less than this number, because we cannot call an irregular pattern of threads. Each block should have same number of threads. So, if you have 1000 threads and 50 blocks, there will be 50,000 threads which will be launched. So, now in case you have 4900, 990 dimension vector, so there will be 10 threads will basically do nothing. So, you have to identify that if ID is less than n, then only the threads will operate, otherwise those threads will not operate. So, n threads will be there which will do computation for the vector addition. The rest threads, there will be at least one block in which some of the threads are inactive. In case the number of block into number of thread is not same as is greater than the size of the vector. So, there will be some threads which will be inactive in that part, but the n of these threads will compute for the vector addition in n different locations. So, we will see what is function execution space specifier, that was underscore global underscore in our previous context. So, global execution space specifier declares that a function is a kernel. What is global? That this function is executed on the device, and device means GPU. This function is callable from the host. So, a function which is called from the CPU and executes in the GPU, that is identified by a function which is executing in the global space. So, it is called from CPU, it is called from CPU, it is executed in GPU. So, it spans over the entire space combining CPU and GPU, therefore, it has a global execution space specifier. Also, in some cases when you do dynamic parallelism, that means CUDA threads are further calling next set of CUDA threads. One GPU is calling another GPU, or one GPU is asking some of the jobs to be executed again in the GPU as a function, then we can use this for compute capability greater than 3.2, we can use device to device call also. So, from one device another device is asked to execute a function, that also can have global execution space specifier. A global function must have void return type, and we have discussed that because we cannot write data in the CPU memory directly from the GPU memory, it always have to be copied back. So, it cannot return any value, it cannot return anything which will be a value and return to the CPU memory. So, it will always return a void return type. Global function, any call to global function must specify its execution configuration. If you remember, in the last slide we discussed execution configuration. Execution configuration tells on how many threads and how many grids and how many what is the grid size and what is the block size, how many blocks and how many threads per block will be there. That has to be specified once a global function is called. So, a global function is a function which will run on a GPU called from a CPU, or in for case of dynamic parallelization called from a GPU and run on a GPU. But as the global function will run on a GPU, it will run in a single instruction multiple thread architecture. Therefore, the total number of threads are to be specified, which can be specified by specifying number of blocks in the grid, that is grid size, and number of threads per block, that is block size. So, that has to be specified through execution configuration when the global function when the kernel function is called. A call to global function is asynchronous, and that is important, that synchronous means because multiple threads will be launched. So, when the function is called, a synchronous function will ensure that all the threads are executed, then only the next statement will be executed by the program. But in case of a kernel call, it is not ensured that all the threads are executed. It launches the kernels. Depending on the GPU scheduler, the threads will be active and they will do the computation. However, as soon as it asks the GPU to run the program in multiple threads, the function returns back to the, the control instruction instance return back to the CPU, and CPU keeps on working on the next set of instructions. So, this is an asynchronous call. It doesn't doesn't satisfy the criteria that all the threads are done and then only the next job will be processed. CPU can keep on processing the next job only once the kernel function is informed to the GPUs. So, in case we need a synchronization, in case we need that all the threads are executed, then only the next step will be done, then we have to put some synchronization barrier. One of the that is CUDA sync threads in CUDA. We will see at some point of time that. The other execution specifier is device, and this is for the function which is executed on the device and the GPU and callable from the device only. Say for example, you take a kernel function itself. Within the kernel function, it needs to call another function. So, it is a function which will be called by the GPU and executed by the GPU we in the same stream of instructions. So, this is identified as the device execution specifier. So, when in the program a function is given with device execution specifier, it is a function which is called by the kernel and will be executed in the GPU only. And when global is given, it is a function which is called by the CPU and will be executed on the GPU. Therefore, it is a kernel function. The global and device execution specifiers cannot work together. A function in together cannot be a global function as well as a device function. Everything is taken from NVIDIA CUDA programming guide. The other specifier is host. What is host? We can understand that when a function is executed at host and called from the host only. So, CPU calls any function that will be executed on CPU. It is not a kernel. A CPU, the CPU C code part calls a function, and this function itself works on the CPU. This is called a host execution specifier, and we can understand that by default any function is a host function. If it is a global function, we have to mention it as a kernel. If it is a device function, we have to mention it as with a device specifier. But if it is a host function, it is by default, if we do not specify anything, we just call the function, it should be a host function. So, in case no execution space is specified, it by default it is compiled for the host and it is called from the host and runs from the host runs in the host only. The global and host execution specifier cannot be used together. Same function cannot be asked to run on both CPU and GPU called from a CPU. So, they cannot be used together. But device and host specifiers can be used together. There are certain cases when we can run a function in both CPU and GPU. So, CPU calls the function, runs in the CPU, GPU calls the function, runs in the GPU. It is possible in certain cases. Well, so, if we summarize it, the execution specifiers gives if it is device and it can return anything. For device and host function, it will be executed on the device, called from the device. So, it is called from the GPU, it is executed in the GPU, and it can GPU can write to GPU memory. GPU function can always write to GPU memory. So, it can return anything, float, double, integer, void, it can return anything. A host is called from host, executed in the host, it also can return any value. But a global is called from a host, or in certain cases called from a device under dynamic parallelism and executed on the device. Now, GPU cannot write to CPU memory, therefore, it should always return a void. These are the three types of execution specifiers. So, whenever we look into a CUDA program, we look into the functions and see what is the execution specifier mentioned before that function, and based on that we identify what type of function is it. Is it a simple function called by the CPU program to run in the CPU? Is it a kernel called by the CPU to run in the GPU, or is it a function which GPU kernel calls and is executed on the GPU? Then these three types of functions are important. These three types of functions are present in the code and they are compiled separately. Their compilations branch out differently. Well, the next part is the execution configuration. if we see the kernel function, when the function is called, we have seen that the function is called within with a syntax within a brace. So, we write the function name is when a kernel function is called. Function name, kernel function means the function which is declared as global in when we write the function. So, function when it is called, it is written function, then this brace 3 greater than 3 less than signs within these certain parameters are passed, and then some of the parameters which are passed or certain arguments are here, and then some parameters which are passed for this function. Now, example is that for the vcad kernel, we have looked into this example. When we call it, we write vcad, then grid size, block size, and we pass the parameters. The parameters that we will be passing are again parameters on the GPU memory only. So, d underscore a, d underscore b, and d underscore c, these are the variable locations in the GPU memory that we pass here. Well, so these are the arguments inside the execution space specifier, and we can see there can be 4 arguments here: dg, db, nss. What are them? The expression in form of dg, db, nss specifies the execution configuration. Dg is type dime3. Dime3 is one particular type of variable in CUDA programming, and it is basically a variable with 3 dimensional non-negative integer value, and it specifies in each dimension it can take it specifies what are the number of blocks or threads in each dimension of that. So, dg is dime3 and specifies the dimension and size of the grid. dgx, dgy, the first component, second component, and third component are the number of blocks in respective dimensions. In x direction dimension, what are the number of blocks, y dimension, what are the number of blocks, z dimension, what are the number of blocks. That will be specified by dime3 dg. So, we can write dime3 dg, and these 3 numbers that will specify that this is the block size here, and then this dg is passed as the block size, sorry, this is the grid size here, this dg is passed as the grid size in the kernel call. Therefore, total number of blocks will be in x direction, number of blocks is dgx or dgy, dgz, their multiplication will be total number of blocks. Similarly, db is also a similar variable of dime3, and it specifies the dimension of size in each block. So, dbx, dby, dbz will equal the total number of blocks. So, we can see that if we launch a kernel which will launch a grid, each kernel will launch an associated grid. Inside the grid, we write to specify the grid size, we write dg 2 2 1. Therefore, 2 blocks in x direction, 2 blocks in y direction, in z direction only 1 block. So, total 4 blocks will be there, and db, that is the block size, we write 4 2 2. So, 4 threads in each block, there will be 4 threads in x, 2 threads in y, and 2 threads in z dimension. So, once we declare this dime3 dg and db value, and we pass dg and db, this particular grid block arrangement will be passed to the kernel. So, the kernel, on how many threads will be launched by the kernel? 4 blocks will be launched by the kernel, and each block will have 16 threads. So, total 64 threads will be launched by the kernel. 64. Okay. Then there are also certain arguments ns and s. Ns is the type is of type size. It specifies the size of the shared memory variable that will be dynamically allocated per block for the call. So, you know that shared memory and L1 cache both are on chip memories, and they share the same space in modern GPU architecture. In case we need some shared memory variable, shared memory means this shared memory is little different than what we discussed about shared memory and distributed memory architectures. This shared memory is the on chip memory, a memory which is shared by the cores present on a streaming multiprocessor. So, when a block will be active on a particular streaming multiprocessor, it can utilize the some of the on chip memory, which is will be very fast, of very fast access. We'll look into shared memory programming in later. And so, ns tells what is the size of the shared memory in byte that the programmer can specify. If nothing is specified, for this case only DG and DB is specified, NS is not specified, it takes it to be 0. There is no shared memory variables that can be declared here. S is the associated stream, identifies the stream. This will not discuss at this stage, but through a CUDA kernel you can launch multiple streams of instruction, and how many streams of instruction that will be launched, that can be specified by S, and that many streams will be launched. But if we do not specify anything, S will be 0, only one stream will be active. So if we do not specify any of these numbers, they will be assigned to the default value. So let us see about the DIME3 variables. So the type of the DIME3 is an integer vector type which is used to specify dimension of grids and blocks, and there is a CUDA defined structure of unsigned integers. When defining a variable of type DIME3, any component we do not specify is initialized to the value 1. So DIME3 is typically, it will take 3 non-negative integer values, and that will give us the number of, say for grid size, it will give us the number of blocks in grid in x, y and z direction. If we do not specify all these 3 values, if we only specify one value, it will take that in x direction, and y and z will be initialized to 1, it will consider that there is no other block in y and z direction. So if nothing is specified, it will stick to the initialized value of 1. So we can see some of the examples. If I write DIME3 grid size 882, DIME3 block size 32/16/4, then grid size means that there are 8 blocks in x direction, 8 blocks in y direction and 2 blocks in z direction. So total number of blocks is 8 into 8 into 2. In each block there are 32 threads in x, 16 threads in y and 4 threads in z. So when we call the kernel, it is launched by 8 into 8 into 2 blocks, and each block launches 32 into 16 into 4 threads. We can see another example for a 2D grid and block. We write that DIME3 grid size 16 into 16. So each grid launches 16 into 16 blocks, and in z direction nothing is specified. So by default there is only one block in z direction, no other block in z direction. It's a 2D arrangement of blocks. Similarly, it launches 2D arrangements of threads per block. If only grid size is specified as only one scalar, block size is also a scalar, so it launches 32 blocks, and then block size is 1024. So each block has 1024 threads. So it's so as simple as that. So you have to define these two arguments, grid size and block size, before calling the kernel, and pass them in the kernel. And these numbers can be, the dimensions of grids and blocks can be anything between 1 to 3. We can see it, there can be 1D grids, there can be 2D grids, there can be 3D grids. Similarly, threads per block also can be, arrangement can be 1D, 2D and 3D. And the total number of threads launched in a grid will be grid size into block size. Number of blocks in a grid, this is the grid size is number of blocks, and this is number of threads per block. And what is a grid? Kernel launches a grid of thread. So the total number of threads constitute a grid, and this is arranged in blocks. A grid can be decomposed in multiple blocks, and then these blocks can be decomposed in multiple threads. Total number of grids is grid size in block size, and number of threads is grid size and block size. That is the number of grids inside the that is the number of threads inside a grid, or number of threads when a kernel is launched. We can quickly see an example that threads, when we launch a grid, and the number of blocks are launched, and when we launch in each block there are number of threads. So all of them are launched together. The total number of blocks are threads, the total number of threads, that is number of threads per block into the number of blocks they are launched. Kernel launches all threads in a grid. So, threads are organized in blocks of grids. Kernel launches all threads in a grid following an SIMT model, single instruction. The instruction is same for all the number of threads. The kernel function is executed into grid size into block size numbers in that many threads. So, each thread is executing the kernel function. So, total number of threads is the total number of execution of kernel functions, but each kernel function is operating on different thread location. It is required therefore, on different thread is tagging with different locations of the memory, because it is again single instruction multiple thread or single instruction multiple data model. So, same instruction is being passed, but each instruction is looking into different location of the memory. So, each of these threads has to be tagged with a particular location in the memory. So, this is device memory, say this will look into a particular location of the memory, this will be tagged to a particular location of the memory, so on. Each thread will take care of a particular location of the memory. So, it is important to find the global ID of the thread from the local ID. Local ID means that local ID of the thread is the ID of the thread inside the block. Global ID is ID of the thread inside the whole grid. So, it is important to find out the global ID of the thread from the local ID in the block and the ID of the block in the grid, in which block it is residing and what is the local ID of the thread within that block. Block size and grid size informations are available in the execution configuration kernel. So, you always specify block size and grid size. Now, local thread ID is given in, if it is a 3D block distribution, by thread ID x.x, x direction, thread ID x.y and thread ID x.z. This is the ID of a thread. This coordinate gives the ID of the thread in the block, in the local block, and the block ID is given, block dimension is given, which is passed through the grid size argument, block dim x.x, block dim x.y and block dim x.z. Block ID is given by this. These are the built-in functions. So, when you call from the kernel, it returns the values of the local block ID, the dimension of the blocks and the local thread ID. Using this, we can constitute what is the global ID of the thread. So, using this set of information, we can constitute global ID. And how global thread ID is important, we can see an example of matrix addition. So, two matrices A and B will be added and we will get C. Now, we pass the number of blocks and number of threads per block, and then we said that number of blocks is 1 only. So, one block is launched and all the threads are in the same block. So, the question can be, I mean, if multiple blocks are launched, then finding the global ID is difficult. Why do we still launch multiple threads? This is due to the fact that as there are multiple streaming processors in the GPU, and one streaming multiprocessor can launch one block at a time. If there are multiple blocks assigned to one streaming multiprocessor, there will be some sequentiality between them. So, we launch multiple threads because all the streaming multiprocessors can be active, each can launch one on its own, more parallelization can be given. But let us see the example, one block is launched and the block has n by n thread structure. So, we find out what is the I gives what is the x ID of the thread, j gives what is the y ID of the thread, and this I and j we relate, we put as a pointer of the memory of the matrix location and use this to find the matrix addition, and this is called thread algebra. We will look into this thread algebra in detail in the next class, that how we can use the local IDs of the thread for multiple block, multi-dimensional block and thread structure, and use them efficiently to point to the memory of the array or matrix which will be operated by the kernel call. Well, the next important part, we understand that when we write a GPU program, we cannot directly talk to the GPU memory. It is CPU which allocates the GPU memory through CUDA, malloc, and copies data from CPU to GPU and copies back data from GPU to CPU through CUDA memcopy commands. So, device memory, GPU memory in CUDA is managed from the CPU only. Only thing is that that operations, I mean changes in the memory, operations in the memory is done through a GPU code, but memory allocations and reading from that memory is done by the GPU only. So, device memory management is an important part in a CUDA code. CUDA provides functions for allocating and managing device or GPU memory from the host CPU. Two important functions are CUDA malloc and CUDA free. Syntax is CUDA malloc, then the void location address of the memory in the device and the size of that memory. When we do that, the CUDA malloc is being executed by the CPU, but it allocates a memory in the GPU. It allocates a memory of size count in the device memory and updates the device pointer that device pointer location with that allocated memory. So, it allocates a memory space in the device memory. Malloc allocates a memory in the GPU's RAM. CUDA malloc allocates the memory in the malloc allocates the memory in the CPU's RAM. Sorry, CUDA malloc allocates the memory from CPU. CPU executes it, but it allocates in the GPU RAM. And once the operations are done, if you have to free the memory, that is CUDA free. CUDA free of the memory location, it deallocates the region of the device memory. They are compatible to malloc and free. Malloc doesn't, these operates on the CPU memory, and these are on the GPU memory, but both are executed by the CPU. So, CPU manages GPU memory through CUDA commands. CUDA program requires data transfer from host to device and device to host because, and the associated workflow, because we cannot directly assign CPU cannot directly write to the GPU memory, or GPU cannot write to the CPU memory. It has to be a data transfer. They are two different physical and virtual memory locations, therefore, there has to be a data transfer across these memory locations. So, if when we run a simple CPU program, the CPU's RAM reads from the main file system, and then CPU's registers read from the RAM and then operates on the variable and again writes back on the RAM. But when we look into a CUDA program model, the CPU's RAM reads from the main file system IO system, and then it copies the memory to the GPU's RAM. GPU reads, the GPU processors reads from the device RAM, GPU's RAM, and changes that memory, and then it is copied back. So, there is a copying to the device, and then again it is copied back to the CPU's RAM. That is the process. And the copying command is CUDA mem copy. CUDA mem copy says that what is first, you have to give the destination address, then source address, then size, and then argument of CUDA mem copy kind, which gives the direction. It is copy from CPU to GPU or GPU to GPU, device to host or host to device. This direction is on which direction this copy is being done. Is CPU copying to GPU or GPU is copying back to CPU. So, SRC is the pointer to be the data to be copied, and DST is the pointer to be destination. First comes destination address, then comes source address. Destination and source do not lie on the same device, because then you do not need CUDA mem copy. Destination, either destination lies in CPU, source in GPU, or destination in GPU and source in CPU. So, destination and source lies in the different devices. And interestingly, this is a blocking thread. So, this can act as a synchronization step. After your CUDA kernels are over, unless CUDA mem copy is executed, none of the executions can flow the next. CPU cannot do anything else, none of the executions can flow. So, this will be, we'll see later, this is acting as a thread synchronization or a barrier after the GPU calls. It does not start until previous CUDA calls are complete. So, all the threads have to come into an end, then only it will start. And this direction can be host to device, CPU to GPU, device to host, GPU to CPU, and in certain cases device to device. For dynamic parallelism cases, one GPU to another GPU, device to device. An example is that in our code we have copied device memory, host memory A to device memory A, and the direction is host to device. Host memory B to device memory B, direction host to device. Then after we calculated C is equal to A plus B, the device vector C is copied to the host vector C, and the direction is device to host. That syntax is given, and this is extremely essential because unless we are not using an unified memory access pattern, these memories are different and we always have to copy from CPU to GPU and GPU to CPU. Well, these are the references, mostly it is taken from NVIDIA's CUDA lecture manuals. We have looked into CUDA installation and compilation. A sample program for vector addition is shown. Execution configuration kernels and thread identifiers are introduced. How to do a very simple rudimentary form of thread algebra, that how global thread IDs are to be identified, are to be found out, and how a thread can be related with a memory location, that is discussed, and then device memory management and memory copying is shown. Okay. Thank you.